You know, in chapter 6, we didn't do all the sections, and we're not going to do all of them in 7 either. But we're going to do two things that are pretty important. We're going to find the area between two curves, and then in the next section, we're going to find volumes of solids. Okay? So, you know, they're not all that difficult. And let me phrase this. They can be really simple. They can also be pretty difficult. The theory, I don't think you'll have any trouble with. Sometimes it's just kind of difficult to find the pieces you need to figure them out. Now, that's the volumes. The areas, they're really straightforward. The area underneath a curve, you can find with an integral, right? So if you're finding the area between two curves, you're finding two integrals and subtracting. For instance, if the area underneath G is, let's say, 7, and the area, I guess that was F, underneath F, and the area underneath G is 3, well, what do you think the area between the two is? It's got to be 4. It's just, you just got to subtract. Okay? So that's really as simple as it is. The area under F is that definite integral. The area under G is that definite integral. Subtract them, and that's the area between those two curves. Now, instead of doing two separate integrals, can't we make that the integral of one of them, of the top one minus the bottom one, and do it as one integral? Now, there may be times it's actually easier to do them as two separate integrals, because we've separated integrals before, haven't we? But there's also going to be times, like if they're both polynomials, you might as well subtract one from the other and just have one polynomial that you have to integrate as opposed to two different ones. So it's the area of the curve that's on the top minus the area of the curve that's on the bottom. That's the area between the two curves. Now, that would work even if you move those curves around, right? As long as they're still the same distance apart, if you took the whole thing and moved it up, wouldn't the area between them still be 4? Or if you move the whole thing to one side, wouldn't the area between them still be 4? Or if you move the whole thing down lower, wouldn't the area between them still be 4? So that's the way it works, top minus bottom. And if you can remember that, you got it. Now, if you also remember, when we first started with definite integrals, we were drawing in rectangles. And sometimes, and this was good stuff on Saturday, I thought, the left Riemann sums and the right Riemann sums. All right, that was good to see that again. So sometimes, you know, depending on where the rectangle is, you're using the right end point for the height. Sometimes it's the left end point, whatever. So, but we were doing rectangles. Well, look, even when you're doing this, you can still have rectangles. Just look where the rectangle is. All right? The height of that rectangle is going to be that y-coordinate minus that y-coordinate. It's going to look a lot like that, isn't it? F of x minus g of x, because f of x will be, I'll call it y2, will be y2, and g of x would be y1. So you're still doing rectangles. And that's going to be even more important when we get to volumes. Okay, there's still rectangles there. Now here's the way I have it written out. The book says this, and they're exactly right. I like this. The area between two curves, if the curve, well, let me just read what they have. If f and g are continuous on the closed interval from a to b, and g of x is less than or equal to f of x for all x in the closed interval from a to b, then the area of the region bounded by the graphs of f and g and the vertical lines x equals a and x equals b is, so there are your boundaries along the x-axis, and then it turns out to be, since g of x is less than or equal to f of x is the top curve minus g of x is the bottom curve. And then, of course, you have to have the dx because that's the width of the rectangle. Okay? All right. And then I just have written out here what we just talked about, how you would just take the area of the top one, the area of the bottom one, get the area between them. It may be better to have it as two separate integrals. it's usually better to have it as one interval. Usually less work. All right? And then that works no matter where the graphs are positioned. Up, move them down, move them left, move them right. As long as you keep that relationship, they don't get any further apart, you've not changed the area between them. Okay? All right. Now, something that's new is they're going to give us functions of y as well as functions of x. Functions of x look like this, right? Functions of y, they'll be like that. They're not going to be functions. They're going to be functions of y. Instead of having a vertical line test to see if it's a function, remember that? As long as no vertical line hits it more than once, it's a function. Functions of y have a horizontal line test they have to pass. No horizontal line hits them more than once. Okay? And so the way that works then is the larger values are to the right, aren't they? Instead of up, they're to the right. So it'll be the curve on the right minus the curve on the left. And everything's in terms of y. That's a dy. Those limits of integration are y coordinates, not x coordinates. Okay? And I'll work an example of that for you. And it's a little weird the first time you try it. But here's what I want you to put in your notes. That right there. And that will be very similar to the way we write our notes when we get to volume. So we're always going to need to be able to draw in a representative rectangle. That's the reason I did it this way. Vertical rectangles. That's when you have functions of x. That's what you're expecting. Horizontal rectangles are when you have functions of y. That's really not much something we've dealt with much so far. Now, how do you know which one you're dealing with? Well, here's how you know. If we've got that and that, draw in a rectangle that's between them. So start with one, draw a rectangle to the other. Now, would the width of that rectangle be a dx, a change in x, or a dy, a change in y? Well, it's from there to there, so that's a dx for the width of that rectangle, isn't it? But if you have something like this, now when I draw in a rectangle connecting them, it's going to be like this. It's going to be horizontal. Okay, what's the width of that rectangle? Is it the change in x? It's a dy. It's a change in y. That's a skill we're going to have when we get to volume. So let's practice it now. Okay? All right, any questions so far? Let's do number 2. Let's see. We're all the way over on page 452. 452, number 2. So, set up the definite interval that gives the area of the region. Well, number 2 says that f of x equals x squared plus 2x plus 1, and g of x equals 2x plus 5. If they do not give you a graph, you graph it yourself. Okay? So, they do give us the graph of each of these functions. And notice that even though when we were setting up the formulas and doing the theory and all, we always pretended f of x was on top, there's no rule that says f of x has to be the function whose graph is on the top. Okay? So it turns out in this one, g of x, the line 2x plus 5, is actually always greater than or equal to the other one. Now, Actually, not quite true. Between where the two graphs intersect, g of x is always on top. Because look, we can't find the area between them except for the place that's enclosed by where they intersect. Now, is there a rule that says they have to intersect? No, but these two do. So if I'm going to find the area between them, it's got to be the area of the region enclosed by those two graphs, and all that region is between the 2 points where they intersect. Okay? So, g of x is the one on top. So let's set up our definite integral. You can write it down below. I'll put it here and then uncover what I've got. So the area equals the integral from, okay, what's the x-coordinate of the point where they intersect on the left? -2. What's the x-coordinate of the point where they intersect on the right? +2. Which curve is on the top? G of x. Minus, which curve is on the bottom? F of x. And now I've disrupted it so much that you can't see it. If I draw in a rectangle, what's the width of that rectangle? Dx. And that last little step right there that seems like it's meaningless, putting the dx, is vital. Because if I've written my functions as functions of y, but then my width of the rectangle is a x, I've done it wrong. Either I'm wrong about the dx being a dx, it should be a dy, or I was wrong about the functions being functions of y. So that's always got to match up. That, and that must match up. Okay? And you know what else has to match up? Whatever that is, those have to be in terms of that variable. Okay? So everything's x's. The functions are x, the width of the rectangle is x, the limits of integration are x. So that's what I wrote right down there. Everybody with me? Okay. Now, that's all they require us to do. Well, I guess we should fill in what the functions are. So, area equals the integral from -2 to 2 of g of x, 2x plus 5, minus f of x, and put it in a parentheses, x squared plus 2x plus 1, close your brackets, dx. And that's all they require us to do for these directions. Set up the definite integral. All right, I did. Any questions? Okay. Now, I'm telling you to go ahead and find the area. The book's not, I am. So let's find the area. So let's actually do the simplifying inside the brackets. All right? Distribute that negative, and you can do it in your head. That'll turn that into 2x plus 5 minus x squared minus 2x minus 1. And what do you end up with when you combine all the like terms? Negative x squared plus 4. So area equals the integral from -2 to 2 of negative x squared plus 4. Okay? So area equals, what is the antiderivative of negative x squared? Negative 1/3 x cubed plus, what is the antiderivative of 4? 4x evaluated from -2 to 2. All right, it's been a while. Do we substitute in the 2 first or the -2 first? The 2. So that'll be negative 1/3 times 2 cubed plus 4 times 2 in our first parentheses. Minus, and then negative 1/3 times negative 2 cubed plus 4 times negative 2 in our second parentheses. Let's work inside our first parentheses. 2 cubed is 8. Negative 1/3 times 8 will be negative 8/3. 4 times 2 is 8. Minus sign. Second parenthesis. Well, cube negative 2, you get negative 8. Negative 1/3 times negative 8 is positive 8/3. 4 times negative 2 is negative 8. Now, I can either finish up by working inside each parentheses, or I can distribute that negative. Is it going to matter a whole lot which method I choose? I don't think it is. So which method do we choose? Finish each parentheses or distribute the negative? Distribute the negative. So we get negative 8/3 plus 8 minus 8/3 plus 8. Okay. So negative 8/3 and negative 8/3 is a negative 16/3. 8 plus 8, 16. So what's 16 with the denominator of 3? It's what over 3? 48. So whatever negative 16 plus 48 is over 3, so that would be 32/3. And then it would be square whatevers, right? They didn't give us any units, and they hardly ever do on graphs, but square whatevers because it's an area. Number 2 makes sense? All right. Let's try number 25. You expected 3 or 4, something like that next, didn't you? Number 25. Sketch the region bounded by the graphs of the algebraic functions and find the area of the region. All right, so if you graph f of x equals the square root of 3x plus 1, the plus 1's not under the square root, it looks like this. You can do that on your calculator. If you graph g of x equals x plus 1, well, that's a line, y equals x plus 1. It looks like this. Now, on the graph that I copy and pasted, it's already got the points of intersection, but we don't know those, do we? So before we can set up the integral, we need to know what the boundaries are. All right, again, these functions intersect each other, so the points of intersection, those are your boundaries. So we need to find the points of intersection. Actually, am I interested in the x-coordinates of the points of intersection or the y-coordinates of the points of intersection? X, because if I draw in a rectangle, the width of it will be dx. So everything needs to be in terms of x. Okay? So let's find the points of intersection. Take your two functions and set them equal. And we'll find the points of intersection. So the square root of 3x plus 1 equals x plus 1. And then solve for x. So let's subtract 1 from both sides. Square root of 3x equals x. Square both sides. 3x equals x squared. Solve it as a quadratic. So 0 equals x squared minus 3x. We're fortunate in that this one's factorable. So 0 equals x times the quantity x minus 3. So according to the zero product property, either x equals 0 or x minus 3 equals 0. So either x equals 0 or x equals 3. So the x-coordinate of one point of intersection is 0, and the x-coordinate of the other point of intersection is 3. Follow me on all that? Okay. So now we know this much. Area equals the integral from 0 to 3. Okay, now, which of these curves is the one on top? The square root of 3x plus 1 or the x plus 1? The square root of 3x plus 1. So instead of writing the symbols f of x minus g of x, I'm going straight to it. So f of x, the square root of 3x plus 1 minus g of x, make sure you put it in a parentheses, x plus 1. And then double checking to make sure we're right, that we've got all this in terms of x. The width of a rectangle is dx. So it's good that everything's in terms of x. That's when you'll know when you've messed it up. If everything's in x, but then the width of the rectangle's got to be a dy. And don't just rubber stamp that. Actually draw your graphs, draw in one rectangle between those graphs, and make sure you know what its width is, dx or dy. Okay? So that gives us that. And that's the integral we want to find. We all agreed that's the integral we want to find? Okay. Well, let's distribute that negative sign. And if I do, 1 minus 1 is 0. So I've got the square root of 3x minus x. But I'm not happy with that square root of 3x, because that makes me think I'm going to have to make a substitution to figure out this integral, but I don't. Because isn't the square root of 3x the same thing as the square root of 3 times the square root of x? And isn't that the same thing as the square root of 3 times x to the 1/2? That I can integrate. Okay? So area equals the integral from 0 to 3 of the square root of 3 times x to the 1/2 minus x. Because remember, 1 minus 1 gives us a 0. All right, now this is going to be a little ugly, but when I use the power rule here, add 1 to the exponent, so now the exponent's 3/2, divide by 3/2, which is the same thing as multiplying by 2/3. So my new coefficient is 2 radical 3 over 3, or 2/3 times square root of 3, however you want to write it, x to the 3/2. Then integrate x, get negative 1/2 x squared, evaluated from 0 to 3. So area equals, then we substitute the 3 in. So 2 times the square root of 3 over 3 times 3 to the 3/2 minus 1/2 times 3 squared. And then, fortunately for us, when you substitute 0 in, you get 0, don't you? Because 0 to the 3/2 is 0, and 2 radical 3 over 3 times 0 is 0, and 0 squared is 0, and negative 1/2 times 0 is 0. It's a big fat 0. All right. Now, since I've got part of this in radical and part of it in exponential, I'm going to have an easier time simplifying it if I either make them both radical or both exponential. I went with both radical this time, which now that I'm looking at it, it seems like it would have been easier if I'd have just done both of them exponential, but oh well, I didn't. So change that 3 to the 3/2. That's really the square root of 3 cubed, and the square root of 3 cubed is 3 times square root of 3. And then that way, those 3's divide out. These square root of 3's multiply together to get you a 3. So my first number is just whatever 2 times 3 is. And probably 6. minus the 9 halves. So 6, which is 12 halves, minus 9 halves is 3 halves. Whatever the unit is, squared. All right, doing okay so far? All right, one more example. You ready for it? Number 27. Same directions. F of y. So what's your first clue that these are going to be functions of y? They're named that. F of y equals y squared. G of y equals y plus 2. So we graph these. And they're difficult to graph on your calculator. Okay? If you're going to, you need to do this. F of y. Now, if it was f of x, wouldn't we call f of x the letter y? So f of y we can call the letter x. You know what I'm saying? So f of y can be rewritten as x equals y squared. Well, if x equals y squared, take the square root of both sides, and y equals plus or minus the square root of x. So to graph it on your calculator, you'll have to graph those two functions. Question? Do what? I don't know how to do that. Maybe everybody else does, but I don't. All right? G of y equals y plus 2 becomes x equals y plus 2, which is y equals x minus 2. So the two functions of y are three functions of x. So here's y equals the square root of x. Here's y equals the negative square root of x. Here's y equals x minus 2. Now, let's go ahead and draw in the rectangle because it's easy to get this one wrong. Remember what your functions are. The red one and the blue one are our functions we're trying to get the area between. Okay? So I've got to draw a rectangle that connects those. So look, you might say, well, okay, a vertical one just like that. That particular vertical one works out all right, but does that vertical one? No, that's no good. That's finding the area between a curve and itself, and that just doesn't seem right. Okay? There's something wrong with that. So, any horizontal rectangle I make, will it connect the blue one and the red one? Any one I make. So it needs to be a horizontal rectangle. Okay? Everybody with me on that? All right, which means dy, which means everything needs to be in terms of y. So even though I did this to be able to graph it, and evidently some of you have calculators where you don't need to do that. If you don't need to do that, don't do it. Just if you can graph them with y as your variable, go ahead. I can't. At least I don't know how to. Okay? So I did all that just to get the graph, but I need everything to stay in terms of y when I work the integral. All right. I need the points of intersection. Now, again, on the thing I copy and pasted, they were already on there, but we don't know those yet. Get the points of intersection by setting the functions equal to each other. So y squared equals y plus 2. Subtract y, subtract 2. Solve this as a quadratic. So when you factor that, you'll get one factor of y minus 2 and one factor of y plus 1. So our two solutions will be 2 and -1. And I attempt at least to write my solutions smallest to largest. Isn't that the way I want to set up the limits of integration? Smallest to largest? All right, I'm almost there. So, area equals the integral. Well, smallest to largest, -1 to 2 of, now, which one's on the right? The blue one or the red one? The blue one. Which one was the blue one? The y plus 2 or the y squared? The y plus 2. So, g of y plus 2, minus f of y squared. And we'd already decided that the width of our rectangle is called dy. Finish it up. See what you get. Everybody able to crunch their way through? All right, let me go ahead and show you what the assignment is, and then I'll put this slide back up. So here's what I want you doing today. On page 452, do 1 through 13 all, and 17 through 31 odd. 1 through 13 all, 17 through 31 odd.